Another common term that we use in our English vernacular is power. Now, power is the rate of work done or the rate of energy expended, which is setting up for our next video of work and energy, a relationship between those. Units for power is watts. And so from this idea, rate of work, whenever you hear rate of something, that means it's divided by time. Where, of course, work and energy have units of joules, and then time has the base unit of seconds, and any joule per second is going to give you a unit of the watt. Now, there's one other equation with power that we need. Let's change our base power equation, rate of work done, so that's work divided by time, and let's actually plug in what work is. So power equals work is a force times displacement, Fs divided by T. And now check it out. You know an equation for S divided by T, displacement divided by time. Let's kind of circle those there. Displacement divided by time is velocity. So that means power is also a constant force you apply to keep an object moving at some velocity. Force times velocity is going to be power as well. So we have three equations. These two really are the same thing, work divided by time, and amount of energy expended, delta E, divided by time. And then power equals force times velocity. All right, a couple of simple example problems here. I have a man pushing a lawnmower. He's going to push this lawnmower 50 meters across his lawn in 20 seconds. And he has to use 75 newtons of force to do that. And the question is, how much power did the man exert? So let's actually, I drew a picture for us really fast, and let's create a variable bank. All right, so I went ahead and created the variable bank and I rewrote the power equation down here. Now notice though, I don't have what work is. I'm solving for power and I do know my time, but I don't know what W is. Instead, I know force times displacement. Thankfully though, we know the equation for work. Work is force times displacement. So then I substituted in F times S, which is the equation for work, in for W, right? Because work is force times displacement. So I replaced the W with force times displacement. Now that leaves me knowing everything. That leaves me now with the ability to substitute in and just solve. So I come out with a power of 190 watts with two significant figures. Now, I use the work equals force times displacement equation inside the power equation. If you would prefer to do that work off to the side, maybe you would write down over here work equals force times displacement, and then work equals 75 times 50, and you then did that math. And then you wanted to substitute that number in, that's perfectly fine also. So if you'd prefer to do side work like that, that's fine. But I do want you to start getting in the habit of it's good to replace variables with their equation inside of another equation when you can. So work is force times displacement. So I can just put Fs in for W when what I know about is my force and my displacement. All right, the next problem, I have a roofer here, going to carry some shingles. The shingles have a mass of 25 kilograms up some 3.5 meter ladder, and is going to do it in 2.5 seconds. And the question is, how much power did he exert? So rewriting our equation, power equals work divided by time, and also we know the equation for work. Work is force times displacement divided by time. You'll see this happens commonly. There are some problems where they go in and they tell you the work. They say the person expended, the roofer expended 250 joules of energy to climb 3.5 meters, or did 250 joules of work to climb 3.5 meters. Well, that's what the work or the energy is. But instead, if we're talking about a distance, that means we're going to have to break this work into force times displacement. Now be very, very careful here. The amount of force needed is not 25 kilograms. 25 kilograms is a mass, not a force. Instead, the force that you have to lift up with is going to be equal to the force of gravity, because to lift something up at a constant velocity, you have to at least balance out F equals ma. You have to at least balance out the force of gravity. So let me repeat that again and emphasize that to you. The force needed to lift something up vertically at a constant velocity, or the minimal amount of force needed to lift something up vertically, is equal to the force of gravity. So that means here, force of gravity is the amount of force needed to lift it up. So I can substitute in for my force of gravity, which then breaks into mg. So now I have, substituting in for force of gravity, mass times gravity, I have mass times 9.81 times the displacement, 3.5 meters, which is the height, divided by time. Another thing that I want to point out, pausing here. Remember, another equation for work or for power is the amount of energy expended divided by time. Well, check this out. How much energy do you have to expend? How much energy do you have to convert? What type of energy are we converting into as we climb the ladder? Well, it's gravitational potential. Equation for gravitational potential is mgh. Here I wrote S for displacement, but this displacement's going up vertically, a height, so we could make this mgh divided by time, the amount of energy we expend divided by time. Well, now I know everything here. I know my mass, 25 kilograms, gravity 9.81, displacement 3.5, and t 2.5 seconds, so I can substitute in my numbers and solve. And with 2 sig figs, I come out with 340 watts, watts being the unit of power. So something that you've seen with these two problems, we can substitute equations into equations. We know what the equation of work is. It is force times displacement. Equation of work, force times displacement, if what we know about is force and displacement. Also, something that we have done before in the past, especially with work, the amount of work that you have done to lift something up, the force you have to use to lift something up vertically is equal to the force of gravity. So you can replace the force used to lift something up vertically with the force of gravity, which then breaks into mg. So never be afraid to substitute equations into equations if that's what you know about. Also, both of these problems were set up to solve for power. That will not always be the case. In many problems, you will be given power, and then asked for, let's say in this one, you were given power, you were given time, you were given how big the lawn is, how much force must the person push the lawnmower with. And so you would have to break work into force times displacement, and you would end up solving for force. Or maybe in this one, how much mass is the man carrying up? If he can exert, if his legs are capable of exerting 340 watts of power, so you'd have 340 in for your power, and he does it in 2.5 seconds, and we know the ladder height, gravity 9.81, how much mass can the man carry up? Or maybe I give you mass, gravity, displacement, and make you solve for time. So just don't automatically assume that all these problems are going to be solving for power. All right, my next problem, I'm going to deal with moving sidewalk. So I have a 2,100 watt motor that causes this moving sidewalk to go. And we don't know anything about how long it is. We don't know anything about how much force it's exerting. Excuse me, we do know about force. We just don't know about distance, and nor do we know anything about time. And we're asked to solve for what velocity does it move it along if this 2,100 watt motor, by the way, motors are most times rated in their maximum power output. So 2,100 watt motor is applying just over 1,050 newtons of force to cause this sidewalk to go. How fast does the sidewalk end up moving? I feel like too often we get away from doing variable banks. Please make sure you go back to variable banks and never really stop them. They become so unbelievably helpful, especially in picking equations, because if you don't do a variable bank, you're going to immediately jump right now to power equals work divided by time, because that's what's kind of stuck in your mind, and then you do power equals force times displacement over time, and then we go, well, I don't know displacement, I don't know force, Mr. Birch, this is impossible, plus it isn't even velocity. Well, that's not right. That's not the equation you would want to use. If you look at your variable bank, you would realize that you need to use power equals force times velocity, because displacement over time, remember, works into velocity. And whenever you pick the right equation, this is a very plug-chug problem. So if you see a power problem that's talking about velocity, please use P equals FV. So after substituting in the numbers, I divide both sides by 1,050. I'm trying to peel things away from my unknown, my variable, right? So I divide both sides by 1,050 to where that cancels out, and that gets me my answer. 2.0 meters per second, because the base unit for velocity, meters per second, and all of my other units were in base units as well, watts and newtons here. So 2.0 meters per second. I needed 2 sig figs, because check it out, 3 sig figs here, sandwich 0, but only 2 sig figs there. Notice there is no decimal after it.